Hope you had a good time at the dinner last night, and I hope you're feeling refreshed. So, as I said in the brief introduction yesterday, there's really two lots of material to cover today. And the first set we started yesterday, which is to look at the sort of more basic aspects of energy harvesting systems and optimizing this concept of how you get the most power density possible from this type of device. And then once we've done that, I want to give you a sort of brief introduction and primer to power electronics in a general sense to start with, and then look at applying that to specifically to some different types of energy harvesting device. So essentially, we finished yesterday talking about this distinction between something that I was calling a direct force type generator and an inertial type generator. And I said to you, this is actually a really important distinction between two different ways of generating electrical energy, and the reason ultimately why the power density is somewhat lower in an energy harvesting device to what you can achieve in something like a large power generation type setup. And this really comes down to the fact that if you're able to grab hold of both sides of a transduction mechanism, then you can put a very large force onto that transducer. And in the turbine hall example here in a power station, then of course you can grab hold of both sides of that transducer, because you can bolt the stator of the machine to the ground and you can attach the shaft directly onto a turbine. So you can get very high forces produced. Once we move to a scenario where we only want a single attachment point, and this really comes down to convenience for an energy harvesting device, then we have to rely on inertia to give us the relative movement between the two ends of the transduction mechanism. So we go on to inertial devices, and I showed you this basic example of this torch yesterday, and ultimately this means that we can get much less force typically, and you can see immediately then that the mass of this inertial element is going to be critical in terms of how much power that we can generate. And of course then, if you want to generate more power from an energy harvester, you can immediately see why the harvester has to be big, because we need more mass in order to get more force onto the transduction mechanism. So if we start to look at this in terms of a schematic then, I think this is exactly where we finished yesterday. I talked about this idea here of this direct force type device, where you've got some sort of transduction mechanism which is converting that mechanical work into electrical energy. And here with a direct force approach, I've got one side of that transducer bolted onto something that is not moving, and then I can grab the other side of the transducer and literally pull this and push it, so I can get very large forces. And of course ultimately, if you think about the conversion here from mechanical domain to the electrical domain, then really I'm interested in integrating the force with respect to displacement. So the bigger I can make the force, then the more energy that I can get. And of course, as I said to you, I'm going to be limited in terms of size, so the displacement, the travel of this is going to be relatively limited. In a MEMS device, the movement that I can get on the transducer is going to be perhaps hundreds of microns, perhaps up to a millimeter, but it's going to be small, and so maximizing the force is very important. And with a direct force device, potentially I can do that. Once I rely on inertia, as I said, the force is going to drop off considerably. If we look at examples of energy harvesting type systems that use this direct force type approach, then there's these training shoes that were done in MIT. When was this? This was probably sometime in the early 2000s, I think. And they had a couple of different ways of generating the power here. I think these particular versions have piezoelectric elements in the sole of the shoe. There were some that had a little rotary generator in the heel, and as you put your heel on the floor, there was a crank that moved this rotating generator. But here you've effectively got this direct force type approach, because you've got the ground on one side that isn't moving on one side of the transducer, and then your body on the other, and you can put a huge amount of force into that, so you're not relying on inertia. Another example here are these ticket gates. This is East Japan Railway Company, and they had these mats in the floor, so that as you stepped on those, you generated some electrical power to power the ticket gates. And again, you've got one side of this that is immovable because it's the floor, and the other side being a person, so you've got a huge amount of force that you can put onto both of these systems, so potentially the amount of power you can generate is very significant. Once we move on to this inertial type approach, And the advantages of this, as I've said, are that we now only need a single attachment point. So we move on to what you would traditionally see as the schematic for an energy harvesting device, which is literally a mass in a box, suspended on some sort of spring suspension. So that in a piezo device is going to be the cantilever substrate material. And then that is doing work against this transduction mechanism, which is what is converting our mechanical work to our to the electrical energy. And so, of course, all I'm doing here is literally is grabbing hold of this external frame and I'm shaking it, and that means that I get a relative movement of this mass with respect to the frame, and so that gives me then a movement that I see from one end of the transduction mechanism to the other. But clearly at this point, the amount of work that I can do onto this transducer is going to depend on the size of this mass. So I'm now restricted very much in the force that I can generate, and if I want more force, I'm going to have to make the mass bigger, and of course that makes the overall device bigger. So you can see, I hope now, very much why there's an intrinsic limit in what I can do with this type of energy harvester compared to what I can do in a more conventional power generation scenario where I can grab hold of both sides of the transducer. So optimizing the value of the force that this damping mechanism produces here is something that is of interest to us to maximize the power density of these devices. Ultimately, the question that we want to try and answer in the course of this lecture is, if I've got a box here that I'm going to fill with an energy harvester, I need to decide how much of that energy harvester is transducer, how much of it is mass, how much what the trade-off is between the actual size of the mass and the motion of the mass. I can obviously make that mass bigger and bigger and bigger and bigger, but as I eventually make it tend towards the size of the box, the movement that I get is going to be reduced. If I have a very small mass, then I can obviously get much bigger travel on the mass within that particular constraint of the volume of the box. And it's the product of the force and the distance that I'm interested in terms of energy. So there's a trade-off there. I probably don't want to make either one too extreme, and we'll have a look at how we get the best out of this type of system. So in terms of inertial generators, some previous examples then, I've already talked about this torch concept where we have a magnet here that shuttles up and down and goes through this coil here. There was a backpack here that came out of Penn State. The idea is you walk along the back of this, the contents of the backpack move up and down, and you can get a little bit of energy generated that way. Apparently this, I mean, when you first look at this, it looks a little bit sort of clumsy, and you think, well, is this really something that you're going to want to carry around, having something moving around on your back the whole time? But apparently it doesn't actually make walking any more difficult because of, I guess, somehow the interaction between the movement of the backpack and the movement of the person. It's not really caught on though, has it? Thinking a bit more about smaller devices, a little bit more along the lines of what we're interested in the ENHANCE project. I mentioned to you a few times yesterday the Seiko Kinetic Watch really is probably the best example of a commercially available energy harvesting device. Does anyone in the room have one, by the way? No. Normally when I ask that question, at least one person has got one. I used to carry one around with me in my bag, but I'm not sure I've got it at the moment. Essentially, if you take the back off one, you see this mechanism, and it's essentially, so you can see here, the face of the watch obviously is circular, and then the mass, the inertial mass in the device is this half circle, and it's connected to a generator here through a high ratio gear train. So you move this mass a little bit and you get very fast motion of the actual generator itself. And so as you tip your wrist from one side to another, this swings around and it generates electrical power. And it's generating a few microwatts typically, and that's all you need for a watch. And actually, it's one of the, I think it was a really well targeted product by Seiko, because if you look at all the stuff that people discuss in the last 20 years about where we can use energy harvesting, people always want to do things like a self-powered mobile phone. People talk about trying to put energy harvesting into laptops. I mean, I understand why we want to try and do these things. It would be fantastic if we could. But of course, it breaks the laws of physics. You cannot generate sufficient power in that particular volume in order to power those types of devices. But actually, the watch is a really nice example because the actual device itself can be fairly large. because of course you have to interact with it as a human, so it requires a face which is big enough for you to read. You don't care so much if it has a bit of weight to it. In fact, the heavier the watch, people would associate it with being a better quality watch. And the power consumption is really in the microwatts. So it's a perfect product to integrate an energy harvesting device. And clearly Seiko spotted that a long time before anybody else. If we want to look then at devices that are tailored for the wireless sensor network, then there's a device here from a company called Perpetuum, which was a spin-out from the University of Southampton. These devices are about the size of one of those small cans of Coke that you get on an aeroplane. So this is the particular model PMG-17, tuned for somewhere between 100 and 120 hertz resonant frequency. Generates in the milliwatts in this particular example with 0.1 Gs of acceleration. So they were looking at putting these devices onto things like induction motors and doing monitoring in process plants. Incidentally, this company, Perpetuum, has moved away from selling purely energy harvesting devices like this, and they now sell solutions of integrated wireless sensing type and diagnosis type solutions. So their CEO really, obviously he wants to make the company profitable, but they started off from a company being an energy harvesting company. And they would not describe themselves as an energy harvesting company anymore. They would describe themselves as a solutions provider. In a particular case here for the rail industry, they're looking at monitoring the condition of bearings in rolling stock on the railways. And traditionally that is often done by looking literally at heat that is coming off the axles on the trains. By the time they get hot though, it's too late, the thing is already failing. So these guys decided they could look at the vibration spectra that is associated with the bearing, and they decided to power that device with an energy harvester. And so at that point, they basically, from just purely trying to sell energy harvesters to selling an integrated system that provides somebody with some useful information that happens to be powered by an energy harvester, where the harvester genuinely makes it a better product, that's the direction they've gone in. So they're selling now services rather than selling energy harvesters as widgets. This actually is a device from Southampton. This came out of a European project that ran in the early 2000s, probably started in about 2001, 2002, called Vibes. That was you can see there's the vibrating structure here, which actually is the coil, and there's a magnet that moves around, and you can see the cantilever there, you can see where it's clamped, and you can see actually that there's quite a lot of circuitry around this. So actually, in this particular case, the actual harvester itself is just this little bit here, but the overall energy harvesting system ends up being this entire PCB. Now, of course, you could make that PCB smaller, but it's important, I think, that you keep in context that these systems really are that. They're systems. An energy harvester, just the transduction mechanism, the mass and the spring, is not a useful device by itself. You've got to have all this other stuff around it before it truly becomes something that you can then power a device from and it becomes useful. Another device here, early device from Berkeley. Shad Roundy is a name that you'll see coming up a lot in the energy harvesting literature. And you see here cantilever, piezo cantilever with a rather large mass on the end. And this gives you maybe some indication of the sorts of aspect ratios that you want to have to optimize these types of device. Of course, remember, the more force you want, the bigger mass you need, and you can see here that's really quite a large mass stuck onto the end of that cantilever. Powers in the hundreds of microwatts. An early device from MIT. This is one of the first, I guess, comb drive based electrostatic energy harvesters. So I'll talk in a little while about the different transduction mechanisms. The idea of this device is to have these variable capacitance structures here. So it's literally a comb type structure, and you can separate the device and put it together again, and you can change the capacitance between one set of electrodes and the other set of electrodes. And if you operate that correctly, depending on what you do, where you put charge onto this capacitor and when you put charge onto it, you can then do work against the electric field and you can generate some power. So this was producing something like, expected to produce something like 8 microwatts at 2.5 kilohertz input. Okay, so just to summarize what we've talked about so far then, this distinction between inertial and non-inertial or direct force type approaches for generating energy is really key to distinguishing what makes energy harvesting different and more difficult than a standard power generation approach. Because as soon as you are not able to physically grab hold of both sides of the transducer, and you can only effectively grab hold of one side of it, and the other side has just got a mass on there which is giving you some inertia to enable you to do work, you're limited then in terms of the power you can generate, because you're limited by the force that you can be producing with a mass, and so you have to then make the mass bigger, but then you make the whole device bigger. So this is really fundamental in terms of the power density of these systems. What we will see actually is that there are optimal forces that we need to decide and operate on the transduction mechanism to maximize the power density. And actually this kind of alludes a little bit back towards what Michael Lallart was saying yesterday when he was talking about these new schemes for switching the charge on the piezoelectric device. That really comes down to trying to optimize the force that is being placed onto the cantilever to maximize the overall amount of energy that is being produced. And as I say, the force, clearly, or the energy that we're able to generate is the integral of force times distance, integral FDR. You can immediately see on this basic mass in a box energy harvesting model that if you make the transduction force too big, then the mass won't move. It'll just stay still inside the harvester and you won't generate any power. But clearly if you make the force too small, then you'll get a lot of relative movement of the mass inside the box. But because the force is small, then your overall power is small as well. So this is why we were interested in optimizing this value. Okay, and we've seen a few examples here of some of the energy harvesters that have already been produced in the literature, and a couple of genuine examples where these devices are now really being used in products, the Seiko Kinetic Watch and this device from Perpetuum, which is now, at least in the UK, is being deployed quite extensively into the rail industry, helping them build a system which monitors the health of the bearings in the rolling stock. Okay, so now I'd like to talk a little bit about transduction mechanisms. There's a paper here that you might want to have a look at that explains some of this, perhaps in a little bit more detail in places. So let's talk about how we're actually going to convert the mechanical work that is being done through the relative movement of the mass inside the box into some useful electrical energy. There are essentially two phenomena that we can use to convert this relative motion into some electrical energy. Electromagnetic, or some people call electrodynamic force, which is really the standard way of generating electrical power. You move somehow a coil in a magnetic field and you put a current into that coil and you get a relative force between the magnetic field and the current carrying wire. So that's just a standard electric motor, either used as a motor or used as a generator. The other way we can do it, of course, is the electrostatic force. And this is what we tend to see in small scale structures, particularly in MEMS. If you look at the basic scaling of the way that forces will scale as you go to small sizes and as you go up to large sizes, there's actually a very famous paper looking at the scaling laws. I'm not sure if I've got a reference into it here. I think the guy's name was Trimmer, looking at the fundamental scaling laws as you change the dimension of a system. And if you look at the way that the electrostatic force scales as you make things bigger and smaller, and you look at the way that the electromagnetic force scales as you make things bigger and smaller, then you find out very quickly why the electrostatic force is something that is of specific interest in MEMS. As you scale things down, ultimately you reach a point where, for a given size of system, the electrostatic force can be much bigger than the electromagnetic force. And ultimately this comes down to things like, if you want to create a force using electromagnetics, you're going to have to run a current in a wire. And eventually you'll be limited by the thermal dissipation of the capability of that wire, and as you make everything smaller, the surface area gets very small, and so you end up not being able to dissipate the energy very well, the heat. So eventually the electrostatic force becomes the dominant one as you shrink things in size. And this is why it's often found in MEMS, whereas it would never be seen, for instance, in a large scale in terms of power generation or large scale actuation. Okay, so the electromagnetic force, as I've said, is typically implemented with a coil and a magnet, and you see lots of people building typically the larger scale energy harvesters using this type of solution. And again, you'll see exactly that distinction. As you build larger energy harvesters that may be of the order of a centimeter cubed or bigger, then this electromagnetic force is something that people look at and take seriously and build devices. If you see smaller devices than that are maybe on the millimeter scale, then typically you'll see that people will be using the electrostatic force because that has become the dominant force as you shrink things down. The way that you can implement the electrostatic type force is either with a moving plate capacitor, as I showed you on this previous slide here from MIT. It could be energized by an external circuit, or it could be primed using an electret, which is the electrostatic version of a magnet. Or it could be implemented using a piezoelectric material. With a piezoelectric material, when you flex it, as you know, you get a charge displacement, you get a voltage. Ultimately, what you're developing then is an electric field in the material, and it's that electric field that you're going to do work against in order to generate electrical power. So one of the questions that we would like to answer, and actually it sounds like a very simple, well, it's a very simple question to ask. It's an incredibly difficult question to answer. Which of these different transduction mechanisms is best? So this essentially comes down to then electromagnetic and then electrostatic implemented either as a parallel plate or cone type capacitor or as a piezoelectric membrane that is attached onto a cantilever. Which of those mechanisms is best for an energy harvester and under which circumstances? Because it's not likely that one of these is going to be best, as I said, across a different ranges of size of these devices and different application scenarios. So, a very simple question to ask, but really a complicated question to answer. And I think actually I'm going to try and help you answer that here. I'm not claiming to give you a definitive answer for any of this stuff. And I think if you look in the literature, this question has been discussed lots and lots in the literature, but you still won't find a really good answer. And that's partly because technology is moving all the time, and if you have a better piezoelectric film this year than you had 2 years ago, then that might change the goalposts as to where the crossover is between the different technologies. But ultimately it's a difficult question to answer because it is not just about how you build this simple energy harvester inside a box, but it depends on how good the electronics is that's connected to it, because that will affect the overall system performance as well. So it becomes really quite an interesting multi-physics problem to try and do this optimization and to pick out what is the best transducer type, what is the best orientation of that to fit all of this stuff into a particular volume. Okay. So if we just have a quick look then at the transduction mechanisms. So the first one and the most, the one that most people will be most familiar with in terms of generating electrical power is this idea of having a coil that is able to move in and out of a magnetic field. And of course, if you make a very abrupt distinction between a magnetic field existing and not existing, so a very high gradient there, then we're able to get a very good change of flux as we move this coil in and out of this magnetic field. And as we move the coil into the field, we'll generate a voltage in that coil, which will push a current around this circuit. And the resultant magnetic field from that current will be such that it will try and stop the relative motion between that magnetic field here and the current that is being produced in that coil. It's fairly easy to calculate in this scenario what the force is, the resultant force on this coil as it tries to move into this magnetic field, because you've simply got this BIL type force that is being placed onto this coil, And so you can easily also calculate the voltage that you get across the coil based on the rate of change of flux and Faraday's law. Once you know the voltage, based on the resistance on here, you know the current, and so you can then, with BIL, you can calculate the overall force. And you can calculate, therefore, that the force depends on the number of turns, the magnetic field, the active length of the coil here that is moving into that magnetic flux, all squared, multiplied by the velocity and divided by the resistance. So clearly, if we put a short circuit on here, then the force goes up because we're able to get a lot of current flow for a very small voltage. So this, you can see, is a damping mechanism. So it's going to be a way, obviously, of taking mechanical work as we move this coil in and out of this magnetic field and then converting it into electrical energy, which in this case is just going to be wasted in that resistor as heat. But of course, we could be using this to charge a battery. And it's important then to be able to understand that this is actually a linear damper, because what we've effectively got is a term here, NBL squared over R, which is our damping constant, and the force is then that damping constant multiplied by velocity. So that's a standard linear damper where the force is proportional to the velocity, and that is the damping constant. So if we use these sorts of systems, these electromagnetic systems, actually many people like using an electromagnetic approach, partly because it then becomes quite easy to analyze, because it's inherently a linear damper. So it's a linear set of differential equations, and it's a nice, easy problem to try and solve. One of the things you will see as we start looking at the other types of damping mechanism, electrostatic and piezoelectric, is that actually we don't have this nice linear damping approach. And so the analysis is a little bit more complicated, and sometimes that can mean that the control of the harvester is a little bit more complicated. So that's probably the first time that I've talked about control of the harvester. What we're trying to do ultimately here, as I keep saying, is to maximize the power density that we can achieve in these devices. And that is going to involve setting an optimal damping force, and setting an optimal damping force in this case means ultimately what can you change here in this device in order to change the damping force. The resistor is probably the obvious thing that you would want to be able to change, not implemented as a resistor, as I said, but implemented as a battery, and ultimately then a circuit which interfaces between the harvester and the battery. And it's that circuit then that we would control in order to be able to change the effective resistance and change the damping that the harvester is seeing, and therefore constantly tracking the maximum power that we can extract from this simple mass in a box. So the electrostatic transduction mechanism then can be implemented, broadly speaking, in two different ways, or two different extremes. Of course, you can move between those two extremes, but typically what you will see for the electrostatic approach is people operating in one or the other of these modes. If you have a parallel plate capacitor here where you separate the plates away from each other and you operate those in constant charge, in other words, you have the capacitor in a closed position, you squirt some charge onto those electrodes so there's a voltage, you then disconnect everything from those, and then you separate the plates so that that charge can't move anywhere, then you generate electrical power, and actually you'll find that the force between those plates is constant. It does not matter about the relative position between the plates, it doesn't matter about the velocity with which the plates are moving apart, you have a constant force. So actually it looks like what we would call Coulomb friction. If you put something on a table and you push it along the table, you've basically got a constant force retarding the movement. Very different to air damping. Air damping is going to be something that is, well, maybe quite complicated to model, but is often modeled as a linear damper, as this type of scenario where the force depends on the velocity. In this scenario, the force does not depend on the velocity. There's simply a constant attractive force between the plates. And that's true also in the sliding type of approach, where we take the plates and we slide them across each other, as long as we operate the system in a constant voltage. So we have, if you think about what's happening here, as I slide these plates away from each other, then the capacitance between these two electrodes is continually decreasing. But if I've got a fixed voltage that I'm applying across those electrodes, then in order to satisfy my simple definition of capacitance, then I've got to be dragging charge off these plates as I reduce the capacitance between them if I'm going to keep them at the same voltage. And so that ultimately means as I start to slide these plates away from each other, charge is going to end up coming off this plate and flowing back into the power supply and therefore charging up the power supply. So that's how I'm doing a conversion between mechanical and electrical work in that particular scenario. And both of these things, both of these ways of operating, the parallel plate separation with constant charge or the constant voltage and sliding type approach, and this of course is the one that the MIT guys had, where they had a whole load effectively of parallel plates there that they were sliding on top of each other in this comb drive arrangement. Both of these things produce a constant force irrespective of the position and irrespective of the velocity. You can control that force depending on the charge that you put on here or the voltage, but it is something that once you've set those electrical parameters becomes independent of what's happening in the mechanical system. So you can calculate that actually by the principle of virtual work, calculate the energy on the capacitor, and you can then take the derivative in order to be able to calculate the force. And so you get this is the force calculation in constant charge, so you can see it is completely independent of the separation between the plates. And likewise also for the overlap sliding type approach, depends on the voltage, depends on a bunch of parameters, but does not depend on how much the plate has slid across itself. It depends on the separation between the plates, but we would try and put this onto some sort of a suspension such that the plates were not able to pull themselves together and they could only move in this sort of motion. Okay, so we can then clearly get energy generation here by changing the capacitance, dragging charge off into the voltage source, or simply storing up energy. So if we have the parallel plate approach in constant charge, we charge these plates up to a low voltage. We then remove all electrical connections so they're in constant charge. The plates move apart, the voltage goes up, and we get then energy generated based on this expression. Okay, so those are the two of the mechanisms for generating electrical energy. The last one, and the one that you've now spent the most time looking at, of course, is the piezoelectric approach, where if we strain a material, then that deformation gives us charge separation within that material, and we get a voltage. So we effectively, as we bend that piezoelectric cantilever, we put charge onto the capacitance of the model for the piezoelectric material. And once we've done that, we've built up a voltage. Then, of course, we can use that voltage to supply an external load. So this model you'll have seen a number of times over the last couple of days as a simple model for a piezoelectric material where we have a current source, and the amount of current that is produced depends on the velocity at which the cantilever is moving. So we have an overall current that will come out of this device here, which essentially is the current that is created by the movement of the device minus the amount of current that is going onto the internal capacitance of the device. So we've got an overall external current of some constant multiplied by the velocity minus the internal capacitor current, C dV dt. And the overall force on the device is something which is dependent as a spring type of expression here, where we've got a force which depends on displacement, and then also an additional force which depends on the voltage that we see on this capacitor. So clearly we've got two effects here that are changing the force that we see on the piezoelectric material. We've got this inherent force here of bending the piezoelectric material with no change in voltage. And we've got an additional force which comes about by the fact that we have a voltage on this capacitor. And so you can immediately see now that we would be able to start manipulating the behavior of this piezo by the introduction of an external system, because I can clearly change the force that the piezo is seeing by putting a voltage on this capacitor, which is this second term here. And of course, this is partly why you can use your piezoelectric material either as an actuator or as a generator, because if you put voltage onto your piezoelectric material, it will bend. And that's something that we're going to make a little bit of use of, the fact that we can change the characteristics of this piezo and the force that it sees with an external circuit by squirting current in and out of here, something that we're going to use to try and improve the performance of these sorts of devices. If we try and look at this to start with, this type of simple piezoelectric model, just in the same way that we looked at the electromagnetic model, by saying let's put a resistive load onto here, that is going to give us some form of electrical damping, and therefore it is going to allow us to convert the mechanical motion of the harvester into electrical energy. Not useful electrical energy, it's only going to be dissipated as heat in the resistor. But as I've said, we can mimic a resistor with a circuit and a battery. So let's assume that we're just going to put a resistor on here to start with. If we use these two equations with a resistive load, then we get the force here in the Laplace domain that we see on the transduction mechanism is given by this. So again, we can see this simple force being proportional to the displacement. So that's our sort of standard spring constant here as a constant part of our system. And another term here, which is going to depend ultimately on the voltage that we see on the device, and the amount of voltage that we get on the device is going to now depend on how much resistance we've got. If we put a short circuit on this device, then of course this V of t here is going to be 0, and we get the short circuit based force and therefore the short circuit resonant frequency of the piezo given just by this first term here. But if we put a non-zero resistance on here, then as we flex this device, we will get some voltage on this capacitor, and that is then obviously going to contribute to the dynamics through this term here. You can rewrite this term. It doesn't necessarily look like it's an obvious thing to do. If you expand this term here in the S domain, and you write this expansion here in j omega, then often we would try and do exactly the opposite in engineering and simplify expressions rather than expanding them. But if you expand this term like this, what you can see is you get a term here which is proportional to velocity. So there's a j omega here, which is like an s, which is our derivative here, multiplied by our displacement term. So this term here, alpha squared r divided by 1 plus omega c naught r squared, ends up being a damping term proportional to speed, where the speed is the z of j omega times j omega. And then an additional spring constant term, because this is all just proportional now to z of j omega. So effectively, as we take our piezoelectric material and we put a resistive load onto it, then we're able to extract electrical power, because the force now that the piezoelectric material sees is a combination of a damping term, which is the thing that allows us to extract electrical power, but also we modify the spring, the stiffness of this device a little bit, and therefore we're going to change the dynamics slightly. And I think this is also something that Michael mentioned yesterday in his talk, the fact that you will change and shift the resonant frequency slightly as you start to load up these piezoelectric devices. And this is one way in which you can characterize that shift in resonant frequency. Okay, so then we can ask ourselves the very simple question, well, how do I maximize the total amount of power that I can get out of a piezoelectric material? Using this simple model, I'm going to put a resistive load on here. If I put a resistor on here which is very small, then potentially I get very large currents, but I get very small voltages. If my resistor is too large, I'll get large voltages, but I'll get almost no current. So the happy medium, where you find that you maximize here the force, is with this value of R being equal to 1 over omega c naught. So I set this value of R here to 1 over omega c naught, and it maximizes the damping force that I get with a piezoelectric device. Now that's very important as an observation, because it tells us really from an electrical perspective what is the best I can do for generating power from this device. But I haven't really considered what's happening, as I keep mentioning, how do I maximize the total amount of power that I can convert in a particular volume, an enclosed volume, with a mass which is going to vibrate inside that volume. And we'll look in a moment at what the equations are for trying to maximize that particular part of the conversion process. And ultimately, that's going to tell us what is the force that my transducer must be able to provide in order to be able to then get the maximum amount of power within a particular volume. Now, at that point, if the force that I need to provide is different to this force in particular, if the force that I need to maximize power generation in a volume is bigger than this force, which is the maximum force that I can provide in my piezoelectric system with a simple resistive load, That's the point where I need to be a bit more clever. I can't just say I'm going to put something onto this that looks like a resistor, either as a resistor or something that mimics the behavior of a resistor. I'm then going to need to put a circuit on there that does something more sophisticated. And that's where you see the sorts of techniques that Michael was talking about yesterday with these strange shaped waveforms on the piezo, effectively able to increase the damping force on the piezoelectric material beyond what you can get with this simple resistive type load. Okay, that's probably basically what I've said here. There will of course be other limits here. There's a limit on the maximum voltage that the piezo film is going to be able to support. So if you bend it too much, you'll either see the material starting to crack, or you might see it break down because of the electric field strength that you're breaching. And then this fundamental limit on how much damping we can achieve with this piezoelectric material. Okay, so just to summarize this particular section, we've effectively got two phenomena that we can use to do transduction from the mechanical motion into the electrical domain, and that's electromagnetic, some people call electrodynamic, and electrostatic. And we implement the electromagnetic in the sort of standard way that people implement large-scale power generation. But of course, we're limited in the force we can achieve because we've got this inertial approach rather than this direct force approach. And then electrostatic, which we can implement either through moving plate capacitors, and there are various ways of doing that, or through piezoelectric material. Each one of these characteristics, as you've seen, is going to have a different velocity force characteristic. The very simple magnet and coil type arrangement, at least assuming that we're operating at relatively low frequency, is going to look almost like a perfect linear damper where the force is proportional to the velocity. The piezoelectric material sometimes can look like that. And as you've seen, it effectively has a linear damping element plus a small correction to the spring stiffness. So you can think of it as a linear damper plus a modification to the spring constant. And the moving plate capacitor is totally different. It's a nonlinear system where you have a constant force irrespective of the position between the plates and the velocity between the plates. So that becomes then a sort of static friction, Coulomb friction, and that means that ultimately the dynamics of the movement of the mass inside the box of the harvester will be very different for the moving plate capacitor approach to what we see with the approach of the other two. And we have to optimize those things because perhaps different types of damping force ultimately can perhaps give us better overall power density, and that's something that we also need to bear in mind. On top of that then, once you've decided what your optimal velocity force characteristic is within the box, then you have to make sure that your transduction mechanism can support that. Can it support the magnitude of damping that you need? And as we've seen with the piezo, there's a very simple way of calculating the limit and the maximum damping force that you can achieve by simply setting the real impedance of the resistor to be equal to the reactance of the capacitor at the frequency of operation. And if you need more force than that, then, as I've said, we're going to have to do something a little bit more sophisticated. So let's talk now about how we do this fundamental analysis and optimization to try and get the maximum possible power density inside this mass in a box. So let's start to think now. We've got this idea of building an energy harvester. We want to build the best energy harvester we can, and ultimately that means, because we're trying to generate power, how do I get the maximum power within a particular volume? And of course, if I can maximize that, then I can either do more with my wireless sensor because I've got more power available, or I can shrink the whole thing, make it smaller and work with a smaller amount of power, but I'm knowing that I'm maximizing what I get in a particular volume. So we go back to this simple model then of the energy harvesting device where we've got this frame here, and that's going to be attached to, in our case here in ENHANCE, to the frame of the vehicle or a part of the vehicle, or perhaps in a tire, in the wheel, but attached to something, and then the movement of that external frame is going to give us excitation into this mechanical system here, and as shown, this is just a simple second order mechanical system of a mass sitting on a spring suspension, and the relative movement that we get of the mass to to the frame is then going to be able to do work on this transduction mechanism. And as we've already seen, there are many different ways of implementing that transduction mechanism. And then in addition, you can change the behavior of that transduction mechanism by putting a circuit onto there and change then the control of that circuit in order to be able to control the characteristics, the force velocity characteristics of that damping mechanism. So how do we then go about saying, well, if I've got a particular volume, how do I get the most power I can in that particular volume? Okay, so let's start with a simpler approach to start with. I know this looks like it's a pretty simple thing. It's a second order differential equation, and it should be pretty straightforward, but for lots of reasons, it ends up being more difficult than it should be. We can start with a slightly simpler type of energy harvester, and sort of go through the very simple optimization end to end here to give you an indication as to what we're going to try and do with the different transduction mechanisms for the vibration type harvester. So here's an example of an energy harvester, and I'm going to call it an energy harvester because, again, it's only got a single point of attachment. It's not a direct force type of device. It's got a single point of attachment, in this case onto a rotating host. So here's a rotating shaft. This could be the shaft of an induction machine, and I want to have, perhaps as an example here, and something that we built, a self-powered wireless tachometer. So I can just glue something onto the shaft of a machine, and it'll tell me how fast the thing's rotating, and it'll generate energy from that host rotation. So I've got here then, this part here is effectively a small motor, which is being used in this case as a generator, and I've got the shaft of that machine, the bit that we would normally refer to as being the rotor, which is being attached directly here to this rotating host. And then I've got the stator of that machine with an offset mass on it, so that I can rotate now the rotor of that machine because it's attached to this rotating shaft. And as long as this offset mass here is big enough, I can now get a relative, I can get a current now that will flow in the windings of this machine. It will generate a force between the rotor and the stator, but as long as that force is less than the gravitational force that I see on the offset mass, I'm able to generate electrical power, and I'm able to generate it continuously. So this effectively is what I've got. I've got a rotating host, I've got a sort of pendulum type arrangement, and there's a torque that's being applied onto that pendulum, and so I've got an mg sine theta term here, which is trying to pull this offset mass here back down to be in the vertical position, but I've got a torque that's being applied onto the rotor of this machine because I'm pulling some current through the windings, and that's sort of tending to offset this mass from the center. So I can see straight away that the electrical power that I can generate from this machine, from this setup, is going to be simply mgl sine theta. And so, is there an omega missing there? mgl sine theta times omega, sorry. So if I want to, so that's the force that I can generate, not the power. So if I want to optimize this, then really I've only got 1 degree of freedom in this scenario. I can change sine theta. So what I would like to do is to be able to have this mass here rise all the way up to 90 degrees, where my mgl sine theta term is the largest. That's when my force is going to be the largest. So that's when my torque is the largest, and so that's when ultimately the power is the largest. So my maximum power is omega times mgl. So it's just torque times angular velocity, and I can therefore find, of course, the maximum torque that I apply is mgl when my sine theta term tends to 1. So that means that I have an optimal amount of torque here of mgl. This actually tends to overestimate, for this particular scenario, the power at low speeds because of friction in the bearings that we're not taking into account, and the winding resistance. But hopefully you now at least see essentially a very basic optimization for this generator. I'm able to choose in this scenario what the force is that I see on this particular energy harvesting device. And so I need to set that force to the point where it allows this mass to rise up to be so that my sine theta term is equal to 1, and that's when I generate the most power. So essentially, if I've got my winding here of this electrical machine open circuit, and I start spinning the host at a particular speed, I'll generate no electrical power. I put a large resistance on there, and I start to generate a little bit of electrical power. As I start to drop the resistance, what is effectively happening is more current is flowing, more torque is then appearing on this structure, pulling this pendulum round, counteracted all the time by this mg sine theta term. But of course, the maximum value I can achieve with sine theta is 1, and so the maximum power I can get from this device is simply when I hold this pendulum here out at an angle of 90 degrees. And that's a very, very simple optimization for one of these energy harvesting devices. And the way that I would control that is by having a variable resistance type device attached to the harvester itself, so that I can control the current that I'm pulling through the windings of the generator and therefore control the torque. So there's very much a system here where I'm using an electric circuit to be able to control the mechanical properties of something. And I know what the mechanical properties are that optimize the power density of this particular structure, and so I need to control the electric circuit to give me the right mechanical properties to maximize the amount of power that I can generate. So if we go back then to our mass in a box vibration type solution, because that is the sort of energy harvester that we're talking about within ENHANCE, then we've got to really make a decision as to whether we're using electromagnetic, piezoelectric, or electrostatic type forces. And if we're going to put our mass in a box, we should also think about whether we make a structure that is resonant or non-resonant. The vast majority of energy harvesting devices are a mass on a spring, and they tend to be tuned to the frequency of excitation. If we're going to really do an optimization here, we shouldn't necessarily assume that that is the best thing to do. Let's take a step back from it and think about whether we really should be tuning to resonance or whether we shouldn't. And then, of course, on top of that, we've got to think about the aspect ratio and the materials and a whole bunch of stuff that goes into the optimization. So, potentially, we've got, if we just break ourselves here into saying that we can either make the device resonant or non-resonant as one option, and then we've got electromagnetic or piezo, which are giving us, broadly speaking here, something that is a velocity force characteristic, which is a linear one. And then we've got the electrostatic type arrangement, which is giving us a very different type of force. So essentially what I'm saying is if we take the electromagnetic approach, we probably have a linear system because we have a damper which is linear. If we take the piezo approach, as you saw earlier, we get something that is not quite a linear system because it's got a small modification to the resonant frequency, but it does have a damping term which is proportional to velocity. So for the moment at least, let's think of that as being a linear system as well. And then the electrostatic one definitely is not, because that is a Coulomb force. The force is independent of the position and independent of the velocity. So that lets us really think about there being 4 different types of ways of building an energy harvesting device. Either it's resonant versus non-resonant, and once we've made that decision, we can implement either of those with the linear type approach, electromagnetic or piezo, or the non-linear damper, the electrostatic damper. When you start to look at this in a bit more detail, it doesn't take you very long to realize that the non-resonant velocity damped approach is not practical to achieve. So if you think about what we're doing here, the resonant system you'll all be very familiar with already. We take a mass on a spring in a box, we shake the box, and we get a relative movement between the mass and the box. And that relative movement is what lets us do work on the transduction mechanism. For a non-resonant approach, then effectively what we're saying is we're going to let the spring constant tend to 0. And we've got a mass in a box, and it's going to basically bounce off the walls of the box. So if I've got this mass in a box and I can sort of jar it very quickly, then I can potentially push the mass from one side to the other, and it's going to strike the other end. And then I've got to shuttle it back, and it's going to zip across the box very quickly. Rather than operating in some sort of simple harmonic motion, it's going to be sort of pushed across, zip across, and hit the other side. And if I want to maximize the power generation from that, then I need to make sure that as it zips across the box, it has the speed pulled out of it so that actually when it meets the other side of the box, it arrives with 0 velocity. Because if it arrives with more than 0 velocity, it means that I didn't pull all the energy out of the mass, and therefore I wasted the opportunity to convert some of that kinetic energy in the mass into an electrical form. Once you think about it like that, you realize that the velocity damped approach is not something that you can really do if you have this non-resonant system. So we end up basically with 3 types of system that we need to analyze. We've got the resonant type approach using the linear damper. We've got a resonant type approach using the nonlinear damper made with the electrostatic transduction mechanism. And then we've got the non-resonant approach with the nonlinear damper. We're not going to look at the non-resonant with the linear damper for the reasons I've just said. You're not able, in that sense, to pull all the energy out of the mass if you jolt it from one side to the other, allowing for the fact that you want to arrive at the other side with zero velocity. You've got to have a force which is not going to be tailing off as your velocity tends towards zero, because otherwise you'll never pull all the energy out, you'll simply strike the other side. And that's why we're going to limit our analysis of the non-resonant to looking at this last line here, the electrostatic damper. So that gives us some terms that we coined back in 2004 for 3 different architectures for these types of vibration-driven energy harvesting systems. Velocity damped resonant generator, so that's purely the linear type system, and it's the basic model that most people will analyze as the first thing they do when they start working on energy harvesting devices. We've then got the resonant approach, which is then Coulomb damped, the non-linear type of damping, typically implemented with electrostatics. We call the CDRG, Coulomb damped resonant generator. Then we came up with something that was a bit different. This was the non-resonant type approach that we wanted to analyze, Coulomb force parametric generator. So we've got basically one linear system here that's resonant, one system here that's resonant but has a non-linear damper, and one system that has a non-linear damper that is also non-resonant. And what we'd like to do now is to figure out which of those is the best so that we can try and build the harvester with the best power density possible. So let's start with the simple VDRG. Hopefully those of you that have been beavering away doing a literature review so far will have seen some of this analysis already. Perhaps if you're on the more materials side you may not have looked at it. If you're thinking more on the system side you may well have looked at it already. If you write down a differential equation for the movement of the mass inside this frame here, assuming that we've got a frame which is excited here through this y of t, we've got a relative movement between the mass and the frame of z of t, then we can write down here mz double dot is minus kz minus dz dot minus my double dot. You take Laplace transforms of this and you get a transfer function between z and y. In terms here now of the resonant frequency of the structure, omega n, and the damping factor, zeta. And you can see here the definitions of zeta and omega n based on the physical constants here in this system. So the physical constants, obviously the mass, and we've said many times if we want to get more power out of these devices, we're probably going to need more mass. The spring constant, K, and also the damping force. And here we're analyzing this simple velocity damped resonant generator, so we're assuming inherently that the implementation of our harvester is one which gives us a damping force which is proportional to velocity, and that velocity is the relative velocity on each end of the transducer and is therefore the value z here, which is the relative velocity between the mass and the frame. So you can see that term there, that's the damping force dz dot, damping force multiplied by, or damping constant multiplied by that relative velocity term. So we end up with this simple second order system as we would probably expect. It's damped. Obviously this term zeta here is the damping factor. You can see here that we can increase the damping factor by increasing the damping constant, but of course given that this is a standard second order system, that damping factor is then normalized by the mass and the resonant frequency. And the resonant frequency is determined as you would expect with all of these systems, root k over m. So if we look at then the frequency response of this system, so this is just looking at the magnitude response here of the transfer function, looking at the magnitude of z of j omega divided by y of j omega, and we look at the peak value of that, we get this as the magnitude response, frequency response of that transfer function z to y. And so that enables us fairly easily to calculate the total energy per cycle that we can draw out of one of these systems. So the total energy is just then the integral of force times distance, as I said. In this particular case, if we integrate from minus z0 to plus z0, where this mass here is able to move to a distance here, minus z0 all the way up to the top part of this, plus z0, then, sorry, that's ZL actually. It's marked as ZL in the diagram and it's Z0 in the equation. So they're the same thing. So we're basically moving a mass from one side to the other. And of course, then we've got two of those, because in a whole cycle we go all one side and all the way back. And it's then just the integral of force times distance. So we've got this dz dot term, which is giving us that force integrated with respect to distance dz. The d is constant, so we pull it out the front of the integral. If we do that integration there, knowing the velocity, we can calculate what the velocity is. We know it's a sinusoidal profile because it's a linear system. We know what the transfer function here is in terms of y to z, so we can easily calculate the maximum speed of the relative motion here, which is related to z naught. And so we can do that calculation and we get this expression here, a very well-known expression for the power generation in an energy harvesting device. So we're basically saying I've got a linear damper, I've got a mass on a spring doing work against that damping mechanism, and that is the maximum, or that is the power that I will generate in my energy harvesting device. So it's dependent here on the damping factor that I achieve, and as we've seen, I can change the damping factor by changing the damping constant here, and we've already seen I can change the damping constant in this case by changing the resistive load on the device. Depends on this term here that I'm calling omega c, and omega c is omega divided by omega n, so it's a normalized frequency to the resonant frequency. So if I'm talking about a device operating at resonance, omega c is going to be equal to 1. So that term simplifies. Y is the amplitude of the input vibration. Omega is the frequency of the input vibration. So you can immediately see now, and this goes back to what I was talking about yesterday, omega here has a very strong effect on the power that you can generate in these devices. We've got an omega cubed term. So as I go up in frequency, my omega cubed goes up very, very quickly and I can generate lots of power. If I go down in frequency, my omega cubed gets small very quickly and I can't generate very much power. So it's very important that I'm very well aware of that, so that I try and operate and design an energy harvester and put it in a location which is going to help me. In other words, if I'm going to put a harvester onto a vehicle, what I'm probably interested in is finding parts of the vehicle that have got a high frequency vibration rather than parts of the vehicle that have got a low frequency vibration. So I'd quite like to pull this expression apart a little bit more and then see how I maximize the total power. I can clearly see then the power is proportional to the proof mass, as we've been saying all along. If I want to generate more power from my harvester, more mass is going to allow me to do that, but of course that's going to make the device bigger. So if I want to find the optimal damping factor, first of all, the optimal value of zeta here, in other words, that's something I can control through changing the load resistance. So if I want to find out that value, I can find it fairly easily by doing dp d zeta, and that gives me a value here for the optimal damping factor, which itself then ends up being dependent on this value omega c, where, as I said, omega c is omega divided by omega n. So it's a question of how close are you to the resonant frequency when you're operating your device. So let's assume that we're operating at the resonant frequency for a moment. So if we're operating at the resonant frequency, omega c is going to be equal to 1. And so what damping factor do we end up with? 0. 0 damping. So that can't be right, can it? Because if there's 0 damping, there's no mechanism at all to extract power from the device. There's got to be some damping, otherwise I can't generate any electrical power. However, that's what the equation tells us, and there's no mistake here in the maths. What is happening, of course, because this is a limit, as you start to decrease the damping factor in this device, then what happens is you get more movement of the mass inside the volume. As I said to you about 15 minutes ago, if I have a force on the device which is very, very large, effectively the mass is just going to stay in the same position inside the volume. So if I've got a very high damping force and I suddenly jolt the box, the mass is just going to move exactly with it. It's like it's bolted into position. and that will generate no power for us. If I start to decrease the damping factor, then as I start to move the box, I'll get some relative motion between the two things, and that allows me to generate power. As I keep decreasing the damping factor, then actually what I find is that the power generation capability of the system keeps increasing. And according to this, in the limit, actually, it keeps increasing all the way until the damping factor goes all the way to 0. Now, that's not something that you can realize in a practical system, but if you keep decreasing and decreasing and decreasing the damping, then the relative movement that you get between the mass and the frame that it's sitting in is going to keep increasing. It's effectively just making a very high Q resonator with a very large gain. And at some point, of course, that will break down. Your spring won't be able to tolerate the amount of deflection that's required. Your mass will move outside of the swept volume. It'll strike the frame of the device. So there are practical limits on this that mean that we cannot set the damping factor all the way down to 0. What it's effectively saying is if we had an infinite volume through which to move the mass, then yes, the damping factor should tend to 0. But of course, as I've said, there's a limit on the total displacement we can achieve. So if we now look at the maximum value or the optimal value of zeta under a displacement constraint, in other words saying, I know I've only got a finite size of box, how far can I move the mass inside the box, and let me optimize that, then, have I got an expression for this? No, I thought I had it somewhere. Sorry, I'm missing an expression that I rather hoped that I had on the slides. I'll find it for you at the break. We can basically now do an optimization here where we allow for the fact that I can only move through a particular distance ZL, and I can then calculate the best value of damping factor, assuming that I'm only able to move that particular distance ZL. So I'm effectively saying I'm going to increase the damping above the damping that is given by this expression to limit the motion of the mass inside the volume to exactly the maximum travel distance that it can have without breaking the device. So once you do that, you can then basically find for different areas of operation of this device the optimum damping factor. And you find that that breaks down effectively to different expressions to define the damping factor depending on what the operating mode of the harvester is. So if I'm operating at resonant frequency, then I'll have one particular constraint. And that constraint typically is going to be that I need to limit the displacement of the device, because at resonance with no damping, the displacement goes to infinity. So I need to increase the damping factor a little bit. If I'm operating away from resonance, then actually I might just be able to use this expression exactly as it is. You can see that I've got a finite value here for the damping factor as soon as I move omega c away from 1. And then that allows you to then plot the performance of these devices on some normalized axes here, and to give you an indication of how much power that you can generate. So what we're saying here, if you look at these axes, quite a lot of information on these plots, and it might take you a couple of minutes to really get your head around it. What I'm trying to do is to plot the performance of one of these energy harvesters over its entire operating envelope, optimizing it at every particular point of that operating envelope. So what I'm saying is I've got an axis here, omega over omega n. So there's a normalization there, which is basically telling me where am I operating with respect to the resonant frequency of the harvester. So I might have designed a harvester to operate at 100 hertz. I might be exciting it at 100 hertz, in which case I'm at the value 1 on this axis. If I'm operating it above its resonant frequency, then I'm operating somewhere up here. If I'm operating below its resonant frequency, I'm operating somewhere down here. So that's that axis. The other axis here is telling me how large the device is compared to the size of the movement that is powering the device. And typically, for an energy harvester, I'll be talking about devices that are relatively big compared to the vibration that is exciting those devices. So if I have a device that might be a centimeter squared, centimeter cubed, it might be sitting on a vibration source which is only moving through tens or hundreds of microns. And that then really is this normalization, z divided by y. So if my device is very large, z was the internal dimension of the device compared to y, which is the excitation of the vibration, then I end up operating along here. If I operate with a device which itself is very small compared to the movement that is exciting it, then I'm ending up on this part of the axis. And you can see now a sort of direct comparison between where you end up on this graph here with the Seiko-Kinetic watch compared to where you might end up in a traditional modern-day vibration harvester. Because the Seiko-Kinetic watch is a device which is, about that size, but I'm exciting it by putting it onto my wrist, and I'm swinging it potentially through quite large movements. So for a Seiko-Kinetic watch, Z is going to be probably quite a bit smaller than Y. So I'm going to be operating somewhere down here. If I'm operating with the traditional sense, with a relatively large harvester and a very small vibration, I'm going to be operating somewhere up here. And what do you see? Well, you see straight away that if you're operating at resonance, then there is significant gain to be had as you make the device bigger than the vibration source that it's powered off. Or if you think about that slightly differently, if I've got a particular size of device and it happens to be bigger than the vibration, so I've got a very small movement of the surface and a fairly large device sitting on that surface, then I can get significant benefit by operating when omega over omega n is equal to 1, because I get this lift here on the surface in terms of the total amount of power, because I'm able to benefit from the existence of that resonance. If I operate above the resonant frequency, which is this area here, then I don't really get any benefit from making the device beyond a certain size. It needs to be a certain size. Once it's reached that size, making it bigger doesn't help, because actually I'm not getting that resonant gain. So effectively what we did here was we looked at every aspect of operation of these devices based on how close it's operating to the resonant frequency and how big it is compared to the vibration source that is powering it, figured out the different operating modes here for what constraints apply in different regions of operation, and figured out the maximum power that can be generated. For this region here where no power is being generated in this particular scenario, for the particular set of practical constraints that were placed into here, we couldn't generate power here because we couldn't achieve a damping force that was big enough. Effectively what's happening, the device here, ZL, is very small. As the device is smaller and smaller, you need more and more damping force, and you get to the point where you can't realize a damping force which is big enough, in which case that meant that from a practical perspective we weren't able to generate power here. Okay, so I appreciate there's actually quite a lot of information on that plot, and I think the best thing for you to do if you're interested in how the detail of how all this analysis is done is to go back actually, and it's a few slides ago now, have a read of this paper. We can talk about it at the break, but that paper has all of the details of the maths as to how this optimization is done. We do the same thing then for the other types of harvester device. So this basically is purely for the linear resonant type device. We want to know how well the other types of device perform. So we start then by also analyzing the resonant nonlinear device, what we call the Coulomb damped resonant generator, which is an implementation, at least I'm pitching to you at the moment, as being an implementation of an electrostatic type of harvester. And the difference now is that this damping force is Coulomb friction rather than a linear type of scenario. I keep saying to you, I'm pitching this to you as the electrostatic implementation with the parallel plate sort of capacitor either moving like this or moving like this in constant charge. Actually, this particular damping type of regime is something that is actually operated also with piezoelectric harvesters, and the technique that Michael Lallart showed you yesterday with the flipping of the charge. So when we looked at the initial equations here for the piezo and putting a resistive load onto the piezo, we said it looks like a system which is a linear system in the sense that there's a damping which is proportional to velocity, and then there's a small tweak to the resonant frequency. That is the behavior of the system with a resistive load. Once you put different circuits onto these harvesters, you can change the force velocity characteristic to some extent as you like, as long as you control the circuit in a way which gives you whatever force velocity characteristic you're interested in. So with this particular type of damper here, the Coulomb type of damper, where we have a constant force which is just resisting the relative motion, what you find if you operate the piezo device using the charge flipping techniques, SSHI, SECE, all those things that Michael was telling you about yesterday afternoon, this actually is the type of damper that you implement. So it's quite interesting to think that the fact that you're changing stuff in the electrical domain is having a direct consequence on the dynamics of what's happening in the mechanical domain. Okay, so if we look at the behavior of this system, then actually we get a describing function here for z to y. We call it a describing function now rather than a transfer function because it's a nonlinear system. A lot of the maths here for calculating the behavior of this system comes out of work that was done, I think, in the 1930s by a chap actually in MIT called Den Hartog. And a lot of the work he did, he was a mechanical engineer, so he was looking at sliding friction, and he would set up experiments where he had an object on a table under Coulomb friction on a spring that was pulling it back and forth, and he would analyze the movement of that and worked out all the maths for it. Quite interestingly, that then 70 years later you can actually apply that same maths to a MEMS device using electrostatic transduction. So you can calculate this, and again, the details of the calculations here are in that paper that's referenced at the start of this section. You can then calculate the transfer between z and y. You can see now that trigonometry starts to come into this, and this gives you all sorts of fun in terms of finding the solutions at different points of the operation of this system. The force the power rather is a little bit easier to calculate in this case because it is literally force times distance. We know the force is constant because that's exactly the definition of the force in this system. So once we know the movement of the device, it's very easy to calculate the total power because it's just simply the total travel of the mass multiplied by this Coulomb force value F multiplied by the frequency of operation, and that's what you get. So there's the power that you can get from this device. You can go through the same set of routines again. We're interested in finding what is the optimal value of force here to get the maximum value of P, assuming that I've got a limitation as to how far the mass can move within a particular box, and then implementing it with an electrostatic type of damper, and this is the sort of performance that you can see. So this is, again, as with the previous damping solution, this particular set of power generation capability is also assuming some practical constraints. So in the previous plot, I showed you that there was an area here, as there is in this plot indeed, where we're not able for the device to operate because we couldn't achieve the damping force that was required before. We've got the same issue here, the same limitation. We've also got a limitation here where we can't generate any more power, where basically we get a flat top on here. So you can see that you get some benefit here from operating at resonance once the device gets fairly big. But ultimately, as it keeps getting bigger and bigger, it doesn't help us. And the reason for that is, from a practical perspective, we reach a point where the voltages that are involved in producing more power as we make the device bigger get higher and higher because we've got more movement. As we have more movement on these parallel plate capacitors, that requires more voltage, and eventually you reach the point where you can't support that voltage because your transistors are not able to support it. But you can basically see that again, you go through the detail of what can be done at every aspect on this whole operating envelope of this harvester, and you're able to then see what the maximum performance is that you can get at different regions of operation. Moving on to the last of these device types, and I think this will be lead us nicely into the break. The last type of device that I mentioned, this Coulomb, this is describing the operating regions in here. Different equations describing the way that you optimize this device depending on where you are in terms of the operating envelope. I won't go into the overall exact detail of all that. You can have a look at it, and I strongly urge you to have a look at the paper, as I say, that's referenced at the start of this section. Let's finish now by looking at the final type of architecture that we identified, the non-resonant type approach. So again, now I'm saying, you know, my first question here was, I've got a particular volume and I'm going to put an energy harvester into that volume. What should that harvester look like in order to maximize the total power that I can generate? And I identified that I could make resonant devices or non-resonant devices, and I could change the damping force characteristic depending on the transducer that I was using and depending on how I operated that transducer. In other words, what electronics do I attach to that transduction mechanism, and all of that I can think about optimizing to do the best I can in a particular volume. So the last of those devices to analyze then is one where I've removed the spring. And the reason for this being something that we might want to look at is simply that if you think about the fact that, and as you've seen on the plots, I'm only really getting a benefit from operating at resonance if my device is much bigger than the vibration that is exciting it. And that is essentially saying if I've got a high Q resonator, then I can exploit the fact that my mass can move through a much bigger distance than the vibration source that is exciting the mass in the first place. Now, if I'm operating in a scenario more like the Seiko Kinetic watch, where I'm putting this relatively small device and I'm exciting it by moving it on my wrist through fairly large distances, then I'm not going to get that resonant gain that I can have in the resonant devices. I wouldn't be able to make use of it anyway, even if I had a resonant device. So maybe I should just simply cut my losses and say, let's forget about resonance, let's not bother with the spring. How well can I do if I literally remove the spring from the system, and I now have a mass which is just able to sort of shuttle up and down a track with no spring. And now the energy is going to get coupled into this mass simply because the mass is going to strike one side of the box, and it's going to bounce off and it's going to be pushed to the other side. It's going to hit the other side and it's going to be bouncing off and hitting the other side. So I'm effectively sort of pushing something and letting it go. Rather than having it on a spring, the mass is going to be against one side of the box accelerates quickly and then stops, and the mass flies away. That's the type of movement that I'm now going to analyze, because I'm interested in seeing, as I said, can this be better, particularly for the scenarios like the Seiko Kinetic watch, where there's no obvious reason for me to use resonance, because I can't make use of the resonant gain anyway, because the device is too small and the movement that's powering the device is too big. So what I did here was to calculate the total amount of energy that you can get per stroke as this device flies from one side to the other. And that really, again, is about optimizing the force. If you make the force too big, then you'll never be able to push the device off the frame. It'll just stay glued to the frame. If you reduce the force a little bit, it'll push away. But again, if you make it too large, it might come back to the same side, and you do a bit of work and then you give it back, and you don't generate any power. What you want is the device to push off one side, the mass to fly all the way, and to hit the other side, at which point you can capture the energy. If you have a damping force which is too small, you push off one side and you smack into the other side, and you've wasted energy. What you want is to be able to push the mass off one side of the device, it flies just across the gap, and it hits the other side just as its velocity goes to zero. So you've extracted all the energy possible from the device. In order to do that, if you're assuming that this is excited with a sinusoidal excitation, there'll be some point in that sinusoidal excitation where this mass breaks away from the frame and flies across to the other side. And that angle here, we're calling this thing beta, the breakaway factor. So it's the fraction of force where the maximum force obviously occurs at the point of maximum acceleration. And it's the fraction of that you want to achieve. If you only break away the mass from the frame at the point where the acceleration is maximum, that means basically at that point there, it doesn't break away. It'll just stay glued all the time to one side. If you break away at half the acceleration, it'll come away here and it'll fly across to the other side. If you break away too early, the force is too small and you go smacking into the other side. So we've got to optimize that value of beta as the fraction of the maximum force that we break away from one side to the other. And that ultimately, if we're going to build this device using some form of capacitance type structure, means setting the correct voltage on the device to get the right force so that I break away at the right time and I generate the maximum possible power that I can. So the total power that I can get is even easier to calculate in this case. Force times distance. The force we're just going to set based on this value of the breakaway factor beta. And effectively then we're interested in maximizing the product of beta times Z0. Z0, or rather 2 times ZL is the maximum distance the mass is able to move, and the force that we're getting depends on the value of beta. You can't solve, unfortunately, beta analytically here, but you can solve it numerically. And you see here that beta itself is dependent on the relative size of the device to the size of the motion that's powering it, as before. So remember, devices that are operating down here on the Z over Y normalization are devices which are quite small, and they're devices that are then quite small and they're being shaken through very large amplitudes. Devices that are up here on this axis are devices that are relatively big compared to the vibration that is exciting them. So they're devices which look to be barely moving because the excitation is very, very small. And as you might expect then, as you get to devices which themselves are very small compared to the movement that is powering them, then the breakaway factor tends towards 1. Because if you've not got very far to move across the gap, you want to do it at the point where the force is maximum and try and move across that air gap with a force which is as big as possible. If the value of Z starts to get bigger, you've got further to move, and if you move with the same large force, you won't make it all the way across the gap, you'll just pull back to where you were. So the optimal value of beta starts to fall. At some point, you have to move into a single-sided operation rather than generating power on both strokes in order to maximize the total power that you generate. And then we look at the total available power that you can get from this type of device. And of course, there's no behavior now that is frequency dependent, because now we don't have a resonant frequency. So if you're exciting this device at one frequency or another, as long as you normalize the power to the power that's available at those frequencies, the device doesn't care whether it's operating at resonance or not, because there is no resonant frequency. You can see here as the device starts to get bigger and bigger with respect to the movement that is exciting it, you get more and more power until a certain point where it decreases again and we don't get any more power. Now, what you remember, hopefully, for these plots that we saw with the resonant type of approach was that when we were operating at resonance, we didn't get very much benefit down in this region of the graph, but as we moved over here and the devices got bigger compared to the amplitude that was exciting them, we got a significant resonant gain. We're not seeing that here, of course, because the resonant gain doesn't exist. So what we can do then is to put all of this together and start to make a comparison as to which of these devices might be best, depending on the closeness we are to operating at the resonant frequency and how large the device is compared to the excitation that is powering it. And what we see is that the non-resonant type solution is very good, as we would have expected, for the regions in Z over Y where the device is small compared to the excitation that's powering it. So if we've got a device that's relatively small and it's going through whopping great big movements in terms of the vibration, so something like, for instance, the Seiko Kinetic Watch fits into that category, then this non-resonant solution is better. And of course, in fact, the Seiko Kinetic Watch is a non-resonant device. There is no spring on that rotating mass inside the Seiko watch. It just flops around on your wrist. So there is no resonant frequency in that device. If we are operating, however, at regions where the device is quite big and the vibration is quite small, then we do get significant gain from operating at the resonant frequency. Omega over omega n is 1. So we can then do rather better by exploiting resonance. If we're operating too far below resonance, then actually, and we've set a device to operate. So if we thought we were going to be operating a device at 100 hertz, we tune our device to 100 hertz, then great, it can work well. It can operate up on this resonant gain here, which goes on forever. But if we designed our device for 100 hertz and we find out that actually in the real operating environment, we only have vibrations of 50 hertz, Or perhaps we put this onto a car engine and we designed it to operate at 100 hertz, but actually if I'm going down the motorway, then I get the 100 hertz. If I'm driving around slowly, I don't get the 100 hertz, I only get 50 hertz. Then unfortunately my value of omega over omega n is going to decrease. I'm going to be operating below the resonant frequency. And then the amount of power that I can get with these resonant structures tails off dramatically. And then the non-resonant device actually then ultimately being the best one under those scenarios as well. Okay, so effectively, if I've got a device which is much bigger than the vibration source movement that is powering it, I should be using resonance. I need to make sure that I don't operate the device below resonance because the power drops off very quickly. I can operate above resonance and still get reasonable power. I just definitely don't want to operate below resonance. So if I'm powering something in a human body environment, like the Seiko Kinetic Watch, the non-resonant system looks better. In something like the ENHANCE project, where we are probably dealing with vibrations that will be smaller, probably an order of magnitude smaller than the size of the device, then we probably want to be using resonant systems. But if we use a resonant system, we need to make sure that we really do operate at resonance or above resonance. We certainly don't want to operate below resonance. We did have a look at the performance of these devices on the human body. So here where we've got non-sinusoidal excitation, we've got something that's a little bit more complicated. And we saw very similar trends to the trends that we've just seen here for sinusoidal excitation. So at scales where the device itself is small, the non-resonant system in yellow here does better. So this is lower body and upper body. And as you get bigger and bigger devices, then you start to see that benefit coming through from being able to operate with some resonance. Okay, I think that's probably a good point to stop. One of the things that I want to do next is to talk about this, how we measure this effectiveness value. As I said, it's quite nice to think that I can make a comparison. If person X makes a harvester and person Y makes a harvester, but they're designed for different applications, and I want it to have a competition, how could I say how good person X's harvester is and how good person Y's harvester is? And once we've got that metric, then we can start to think about, obviously, for our own designs, trying to make things as good as possible and maximize that metric within our own application. So we'll talk about that first thing after the break. Thank you very much.